Hello everyone. We are Group 2 Shreya Channapragada and Samhita Reddy Marepalli, and today we'll present our project, a data-driven study of agro-food CO2 emissions and sustainability. In this project, we focus on emissions that come from agriculture and food systems, basically everything from fertilizer use and livestock to food processing and transport. These activities are a major component of global greenhouse gas emissions, but the raw data is messy and not very user friendly. Our goal was not just to run a few models, but to build a complete from scratch analytics system around FAO stat style data, a Python pipeline that cleans and models the data, a forecasting and scenario module, and finally an interactive Flask dashboard that lets users explore results visually. Over the next few minutes, we'll walk you through the motivation, related work, our dataset, and methods, the three models we implemented, the forecasting scenarios, and a lifestyle demo of the dashboard, and then we'll wrap up with key conclusions and ideas for future. Here is the outline of our presentation. We'll start with an introduction where we motivate why agro-food CO2 emissions matter and what gaps we observed in existing tools. Then we'll briefly cover related work, summarizing four strands: emission processes, global databases like FAO Stat, forecasting frameworks, and machine learning approaches. Next, we describe the data set and problem formulation, and then explain our methodology and pipeline, including pre-processing, feature engineering, and train validation test splitting. We then introduce the three models we implemented from scratch: a linear OLS model with country and year fixed effects, a custom random forest, and an XGB style gradient boosted tree regressor. After that, we present results and insights, model performance, cross validation, feature importance, sector level analysis, and scenario based forecasts. We'll then show Flask dashboard demo, which makes all of this usable for a non technical user. Finally, we'll end with conclusions and future work. Why study agro food CO2 emissions? Agriculture and food systems are responsible for a substantial share of global greenhouse gas emissions. These come from many sources: soil processes, fertilizer application, manure management, land use change, energy used on farms, food processing, and transport. Because these processes are biological and economic, they interact in complex ways. Policymakers and researchers therefore need data driven tools that help them understand which drivers matter most, how countries compare, and what might happen under different mitigation actions. Large databases like FAO Stat provide country year emissions, but as we mentioned in the paper, just staring at raw tables isn't very helpful. It's hard to see patterns, compare sectors, or run simple what if scenarios. So, our motivation was to take something like a FAO Stat style CSV and turn it into a reproducible machine learning pipeline and interactive dashboard that a student, analyst, or policymaker could run locally. We want a system that goes from raw CSV all the way to interpretable insights and lightweight forecasting. Our contributions can be grouped into three main pieces. First, we built an end-to-end pipeline in Python implemented in a single script called dmpro.py. It handles cleaning, feature engineering, model training, evaluation, feature importance, and forecasting. Everything is reproducible and runs with one command. Second, we implemented three predictive models from scratch: a linear OLS model with country and year fixed effects, a random forest CO2 model built on our own cart implementation, and an XGB style gradient boosted decision tree regressor, again using our own cart trees. Third, we go beyond just prediction. We compute permutation based feature importance, group those features into sectors like fertilizers, livestock manure, and food transport, and perform scenario based forecasting for 5 future years. All outputs are then exposed through a Flask dashboard where users can see KPIs, a world heat map, country level trends, and feature importance plots. Overall, the contribution is not just a single model, but a complete teaching scale decision support system for agro food emissions. We organized the related work into four strands, which will summarize them briefly. First, emission processes and drivers. Studies like Gopi and Bikram's literature reviews how agricultural soils emit CO2, CH4, and N2O, and they emphasize roles of fertilizer type, tillage, soil moisture, temperature, and livestock. This motivates our focus on fertilizers and manure in our features. Second, global databases. FAO Stat and similar datasets provide country year greenhouse gas emissions across agriculture, land use, and forestry. These are used in many macro level studies, and our dataset is derived from these tables. Third, forecasting and modeling frameworks. For example, EU level time series studies and unified projection frameworks across 173 economies. These works inspire our simpler trend and scenario analysis, although we operate at a course project level rather than full integrated assessment. Fourth, machine learning and feature selection. Recent papers use ML models and selective feature scoring for emissions prediction, highlighting the need to identify stable influential drivers. Our project aligns with this by using permutation importance and by aggregating features into interpretable sectors. Where we differ is that we package all these ideas into a single runnable from scratch system. Here we highlight what gap we are trying to fill. Existing research typically looks at either single models or purely econometric frameworks. What is missing is a hands on integrated system that a student or analyst can run locally. Our system combines multiple models, OLS, random forest, and GBDT implemented from scratch in Python. It includes transparent permutation based feature importance and section wise grouping so we can see not only which variables matter but which sectors dominate. It builds cross model consensus rankings so we can compare importance signals across algorithms rather than looking at each model in isolation. And it also adds scenario forecasting and a web dashboard, which most academic papers do not provide. So, the main gap we address is the lack of a reproducible end to end ML and visualization tool around FAO stat style agro food emissions data, useful both for teaching data mining concepts and for exploratory policy analysis.
This slide summarizes the concrete objectives we set for ourselves. First, we wanted to build the entire analytics pipeline using a single script, which is dmpro.py, from scratch, avoiding high level skitlearn implementations for the core algorithms. That means we've coded our own card trees, random forest, and an XGP gradient boosting implementation. And then we aim to implement three regression models and evaluate them with a set of metrics, which are RMSE, MAE, R square, F1 macro, and F1 weighted, where F1 is computed after binning emissions into turtles. Third, we wanted to integrate temporal and spatial structure by adding lag features and country fixed effects so the models can capture both history and country specific offsets. And then we wanted a strong interpretability through permutation based feature importance sector level grouping and consciousness ranking across models. Finally, we wanted to surface all these outputs into a flash dashboard showing all the KPIs, a global heat map, model metrics, and feature insights so that the system feels like a small decision support tool rather than just a notebook. Our dataset is derived from FAO stat style agro-food emission tables. So each row corresponds to a country year and includes the total agro-food CO2 equivalent emissions, plus many sector specific variables such as fertilizers, manufacturing, manure management, rice cultivation, food processing and transport, and also land use. So in dmpro.py, the function load and preprocess handles all the preprocessing. So basically, it standardizes column names by removing weird spaces in characters and converting them into underscore separated tokens so that they are safe to use in the code. It imputes all the missing values using median for numeric columns and mode for categoricals, which keeps the distribution stable and is robust for a core skill project. So, we if we enable use lags, it creates a lagged feature like total emission lag 1, fertilizer manufacturing lag 1, and food transport lag 1 per country sorted by year. So, this lets the model use last year's emission and key drivers without needing full time series models. It one hot encodes the country column area into 180 plus country dummy variables, dropping one baseline to avoid collinearity. So this act as a fixed effects. Finally, it assembles a feature matrix X and targets vector Y, where X coordinates numeric drivers, years, and lagged features, and also country dummies, and Y is always the total emission. So, this is about the data preparation and engineering.
Our first model is a linear OLS regression with optional intercept plus fixed effects. We implement it in the class OLS fixed effects. Given a feature matrix, we optionally add an intercept column and then solve the normal equations using the Murray-Penrose pseudo-inverse. Conceptually, this model uses year to capture global temporal trends in emissions, for example, technology or policy changes over time, and country dummy variables as fixed effects, which capture average emission differences between countries that aren't fully explained by the numeric drivers. This provides a transparent baseline. We can interpret coefficients, we know it's linear, and it is fast to train. It also helps us check whether our tree based models are giving reasonable magnitudes. In the results later, we'll see that OLS actually performs surprisingly well in terms of RMSE and R square, but sometimes struggles with ranking tertiles for some countries.
The second model is random forest CO2, a custom model that is built on our own cart regressor class. So each tree is trained on a bootstrap sample of the training data, and at each node, the cart algorithm, which randomly selects a subset of the feature and then tries the candidate thresholds and then chooses the split that maximizes variance reduction in the target. Here we control complexity using parameters like number of trees, maximum depth, minimum samples per second, and leaf size. And then we use cross validation to select moderate values, roughly around 80 to 150 trees, with depths around 6 to 8, which perform well while keeping the runtime manageable. So, random forests are actually good at capturing nonlinear interactions, like, for example, how fertilizers use and livestock interact with the climate variables, and they are naturally suited to mixed numeric plus dummies features. However, as we'll see in the results, our tuned random forest sometimes underpredicts very high emission countries, leading to a higher RMSE and a weaker F1 scores compared to the boosting. The third model is our XGB style gradient boosted decision tree regressor. Instead of actually training many independent trees, gradient boosting trains trees sequentially. So we start with a base prediction equal to the mean of y. Then at each iteration, we compute residuals, which is equal to the actual minus the current prediction. So we train a shallow cart tree on a subsample of rows and a subset of columns using the same cart regressor, and then we add the tree's prediction scaled by a learning rate back into the overall prediction. So by choosing relatively shallow trees with a depth of 2 or 3, around 80 to 120 boosting rounds, and with the learning rates between 0.05 and zero point 0.1, we are able to get a model that actually captures complex nonlinear relationships without overfitting. So we don't implement the full XGB boost regularization math, but in practice, this GBDT behaves similarly. So it corrects residual errors step by step and tends to produce smooth, accurate predictions on the tabular data. But in our experiments, the model gives the best overall RMSE and strong F1 scores, making it our main preference for forecasting. Beyond fitting models on historical data, we wanted a simple forecast, scenario based forecasting capability. So, this is implemented in the function forecast future in the dmpro.py file. So, the idea behind it is that for each country, we take the latest year in the dataset and its feature values. We then define three scenarios, the first one being the baseline, where the drivers stay at the latest levels, the second being a low fertilizer, where the fertilizer related variables are scaled down. Example, it is multiplied by zero point 0.9. And the third one being a high transport, where the food transport related variables are scaled up. Example, it is multiplied by 1.2. Using the lag features, we run the models forward for H years. So here we have kept the default as 5, where each year's prediction becomes the lagged input for the next year. So, for each combination of scenario and model, we store all these predictions into a forecast underscore raw.csv file and then aggregate them into a forecast global trend.csv. We also save scenario specific CSVs like scenario low fertilizer.csv. So these are simplified forecasts, not policy grade projections, but they demonstrate how data mining models can be plugged into a what if analysis and used to reason about the impact of changes in the key drivers.
For evaluation, we use a 60-20-20 train validation test split implemented in train val test split. We shuffle indices, allocate 20% to test, then split the rest into validation and training. On the held out test set, we compute RMSE, which penalizes large errors strongly, MAE, the mean absolute deviation, R square, the fraction of variance explained, and F1 macro and F1 weighted, where we first bin emissions into low, medium, high using tertiles computed from the training labels. The F1 metrics are interesting because many policymakers care more about whether a country is a low, medium, or high emitter rather than the exact number. So we check if the models preserve that ranking. All metrics are stored in a CSV called metrics.csv and later shown in the dashboard. This consistent evaluation across models lets us compare not only accuracy but also classification quality and runtime. Now we'll summarize the key performance results from Table 1. For the linear OLS fixed FX model, we see RMSE around 360 and R square basically 1.0 and high F1 scores close to 0.97. This tells us that the combination of year and country fixed FX plus drivers lets a simple linear model fit the data extremely well, at least numerically. For the random forest CO2, even with a tuning, we get R square approximately 0.983, but RMSE jumps to about 34,600 and F1 scores below 0.50. Qualitatively, the forest tends to flatten extremes and underpredict high emission countries, so it struggles in the tail of the distribution. For the XGB style GBDT, we get RMSE around 18,500, R square approximately around 0.995, and F1 approximately 0.95, which is strong. So the boosting model manages to keep error low while correctly ranking countries into tertiles. Overall, we conclude that OLS is a strong linear baseline and very interpretable. Random forest is somewhat unstable for this task, and the GBDT offers the best trade-off between accuracy and ranking, making it our preferred model for forecasting and scenario analysis. Beyond metrics, the pipeline generates a lot of supporting artifacts that are useful for interpretation and for the dashboard. Every run writes metrics.csv, which is the table of model performance. Feature important CSVs per model and grouped sector importance. It also runs consensus CSVs that combine rankings across models. It also runs KPI files like total emissions.txt, average emissions per country.csv, and top emitter latest year.txt. And also a world heat map in PNG form showing the spatial distribution of emissions in the latest year. If we enable cross-validation, we also get CV results.csv and bestparams.json for random forest and GBDT. Finally, the forecasting module writes forecast raw.csv, forecast global trend.csv, and scenario-specific files. All of these artifacts feed into the dashboard or can be used for further analysis, making the system feel more like an analytics product than a one-off experiment. This slide corresponds to our permutation importance results. The idea is straightforward. We compute a baseline RMSE on the test set. Then for each feature, we randomly permute that column, destroying its relationship with the target. We recompute RMSE and see how much it increases. The bigger the increase, the more important the feature. We repeat this a couple of times to average out randomness and then sort features by RMSE increase. Across all three models, we find a consistent pattern. Fertilizer related variables like fertilizer manufacturing are almost always at or near the top. Livestock and manure variables such as manure management or manure applied to soils are also highly important. Certain land use or forestry variables and year plus some country dummies also carry a strong signal. When we aggregate features into sectors like fertilizers, livestock or manure, food transport, and so on, these sectors dominate the total importance. This matches what the domain literature reports. Fertilizers and livestock or manure are major drivers of agricultural emissions. These importance plots are also exposed in the dashboard so users can visually inspect what each model is relying on.
Here we have a high level view of the system architecture. The backend is essentially the dmpro.py script. The main function run ties everything together. So basically, it loads and pre-processes the CSV, splits into train, validation, and test sets, trains all three models, computes metrics and feature importance, build cautiousness tables, generates KPIs, produces the world heat map, and optionally runs forecasting. So all the outputs go into the results folder. On top of that, we have also built a Flask app which is app.py with three main pages. First being the overview page, which shows controls for selecting the CSV and toggling lags, KPIs, the model metrics table, and the world heat map. When the user clicks the recompute, Flask launches dmpro.py as a subprocess and logs output to the last runlog.txt, and the next being the country drill down page, which lets the user select a country and sees its emission trajectory over the time as a plotly line chart, and the third page being the feature importance page, which lets the user choose a model and see a horizontal bar chart of the top 20 emitters, features by permutation importance with a link to download the full CSV. So the front end uses the Flask and a small custom CSS file for styling and giving a clean card based layout. So overall, we wanted to have the architecture to be simple, transparent, and easy to rerun. Now we will show you the demo of the app. So, in this demo portion of the video, we would like to walk through a typical user workflow. So first, we are running the pipeline from the command line in the Anaconda prompt. So this is the command line that we will be using. So after running, this command line runs the full end-to-end analysis, which generates all the results, and it writes them to the results directory. As you can see here, all the evaluation metrics are done for all the three models that we have used, and all the results are saved into the result folder. Next, we start the Flask app with the python app.py. This is the command line that we are using here, same in the Anaconda environment. And after that, it will open on the local host. So this is the local host that we are using. Uh, so this is how our dashboard looks right now. This is the over page. So here, as we can see, we have a CSV path to put whatever CSV that you would like to compute. And we also have the lag features. We can toggle that. We can increase the lag features, and then we can recompute the uh, entire overview page. Coming to the model metrics, here the model metrics are computed and it is shown here. We can download the metrics.csv file, and also we can view the world heat map of the latest year, which was 2020. Here too, we can download the PNG file, and it also shows the global total emissions, the average per country emission, and also the total emitter, and also the total value in 2020. So this was about the overview page. And then the next page is the country page, where it has the country drill down. It We can select a country like India or the United States, and which shows the emissions that have evolved over time. So you can select any country here, let's say Argentina, and you can click on view. We'll be able to see the emissions over time of for the country Argentina from the year 1990 to 2020. And coming to the features part, the third page. So here we have done a feature importance page which picks the model. We have three different models. So we can pick any model and we can load the model. So it will show the top 20 features for that model. And also, it is a downloadable file. You can download that in a CSV. So this is about the app.
To conclude, we'll recap what this project achieved. We built a complete reproducible pipeline that takes FAO stat style agro food emissions data, cleans and augments it, trains three different models, evaluates them, computes feature and sector level importance, and generates simple scenario based forecasts. All of this is exposed via a small but functional Flask dashboard. In terms of modeling, we found that the linear OLS fixed FX model is surprisingly strong and serves as an excellent interpretable baseline. The random forest has reasonable R square but struggles with extreme emitters, leading to higher RMSE and weaker F1. The XGB style GBDT provides the best overall performance, lower RMSE, and high F1, and is our preferred model for forecasting. Our permutation importance and sector analysis consistently highlight fertilizer related and livestock manure related variables as dominant drivers, which agrees with the broader literature on agricultural emissions. The scenario module, although stylized, shows how reducing fertilizer intensity or increasing transport activity can change future emission trajectories. And the dashboard turns complex outputs into accessible visual insights, supporting learning and exploratory decision making. Overall, the project demonstrates how data mining, interpretable ML, and interactive visualization can be combined to support sustainability questions in agro food systems. Finally, a few directions for future work. On the data and features side, we could integrate socioeconomic variables such as GDP and population as suggested by global emission studies. This would let us study emissions per capita or per unit of economic output and maybe explain some of the country fixed effects. On the modeling side, there's room to explore more advanced feature selection and interpretability methods, for example, penalized regression, SHAP values, or stability selection, which could complement permutation importance and give more robust explanations. For scenario analysis, our current shocks are simpler percentages. A natural extension is to design more realistic scenario generation frameworks, possibly informed by integrated assessment models or policy pathways, and to expose these scenarios interactively in the dashboard. Finally, we would like to expand the dashboard interactivity by adding controls for selecting a scenario and model and letting users compare scenarios side by side and enabling custom sector groupings or region filters. Overall, we see this project as a starting point, a course scale prototype that can be extended into richer decision support tools for agricultural emissions and sustainability analysis. Thank you.